So welcome back. We're going to continue to talk about equilibrium. In this next segment, what I really want to focus on is what is the real true meaning of an equilibrium constant? Let's start off reviewing here. K is an absolutely unitless number. It does not have a unit with it. Remember that when we are actually making K, that it's the balancing act between two kinetics forces. The speed of the forward reaction is going to be the same as the speed of the reverse reaction. The rate forward equals the rate reverse. That's the definition of equilibrium. And because we're putting these two rate laws in juxtaposition with one another, the units cancel out. Very convenient. Second of all, why do we even care about an equilibrium constant? Well, K is a very convenient number that lets us figure out how far a reaction is going to be bending toward one side or the other. Just based upon the value of K, we'll figure out, is it going to proceed far to the product side, or is it going to remain far to the reactant side? Let me give you an example here. Here's just a skeleton for an ordinary chemical reaction. A plus B makes C plus D. We would calculate the equilibrium constant by taking the concentration of the products divided by the concentration of the reactants. So if I would actually see that the reaction is proceeding far toward the product side, once that equilibrium is established, then I would know that I would have a ton of products, because that's the numerator, and very few reactants, since those are the denominators. Our K value, therefore, will tend to be very, very large. So large K values are indicative of reactions which proceed far to the product side. In like manner, if we take a look at the same chemical reaction, and this time let's pretend the reaction will proceed far toward the reactant side of things at equilibrium. Well, that would mean then that I have not a ton of products, but I would have a lot of reactants. K in that reaction would be very, very small. So a small K value is indicative of a reaction that remains more at the reactant side of things. We're not going to make a ton of products. This is why K is absolutely super convenient. So simply by nature of the number, you know a little bit more about the chemical reaction itself. Now another little bit of reminders. In equilibrium systems, equilibrium really wants to be maintained. And it will tend to react to changes, sudden changes, in a way that will restore that equilibrium. Now, one of the biggest things that we've investigated already is concentration stress. So if I increase or decrease the reaction of a concentration of a reactant or product, the system will tend to react to eliminate that stress. Let's look at an example. Again, let's take a look at A plus B makes C plus D. Well, what happens if I increase dramatically the concentration of a product? Now, our equation already doesn't look very balanced anymore. We have disturbed the equilibrium. So in order to regain that equilibrium, the system will tend to speed up the reaction, which will maintain that equilibrium again. We'll get you back to that perfect balance. In this case, because I increased the concentration of a product, the reverse reaction will increase until slowly but surely that balance is going to be maintained by that value of K. We have to continue until we hit that value of K once again. So slowly but surely, your products will start to disappear. You'll get more and more reactants until finally you have balance again. Let's take a look at another example. In this case, actually, why don't we decrease the concentration of a product? Either we're scooping it out of the reaction or adding in another chemical which will precipitate it out in a way. Well, in this case, the reaction would start to move toward the product side. So the forward reaction rate will increase to help restore that equilibrium, and it'll make more products. So slowly but surely, over time, we'll have less and less reactant and more product to try and fill in the gap that we just created. And again, balance is restored once those concentrations, and you would plug those in, mimic the value of K. And then at this point, the rate of the forward reaction and the rate of the reverse reaction will go back into being in balance. Now, what's interesting about equilibrium is that there's constantly reaction happening. Reaction never stops. It might look like it from the outside or looking in because we're not making any more product or any more reactant, but it's constantly fluctuating between those two states. Okay, now just as a reminder, this reaction to stress is known as Le Chatelier's principle. And essentially, that simply means that the system will respond to stress until that equilibrium is maintained. But what's interesting is now we actually have a number to support that. So we know that it's going to continue to do so until all of the concentrations are going to be able to plug back into that equilibrium calculation and perfectly equal that K value. So silly question, but how can you actually tell if you're at equilibrium? Well, one way is to literally be told that you're at equilibrium. Here's an example. We have an equilibrium system, A plus 2B makes C plus 3D, and it says simply that the following system is at equilibrium, and it's found to have the same concentrations. Here they're listed below. And it asks, what's the value of the equilibrium constant? This is a pretty standard problem. Well, the first thing that you're going to want to do is to write out the equilibrium expression. In other words, the formula for how you calculate the equilibrium constant. This is called, again, an equilibrium expression. Now notice, because these are built off of rate laws, we can assume that this is a one-step mechanism. The coefficients become superscripts. That's really important to remember here. It's one of the first things that's going to slip out of your mind. Time to plug and chug. So we simply plug in all the values that we were given, and then we're going to chug out an answer. In this case, our K, or Kc, which is the equilibrium constant with respect to concentration, is going to equal 0.21. Careful, sig figs do matter, and notice there's no unit on the number because K is unitless. So again, the value of K represents a balance between the reactant and the products, and the system is going to fight to maintain this value. So if you're stressing it, either the rate of the forward or the reverse reaction, depending on what you do to it, is going to speed up to maintain that balance and move back toward that perfect K value. Well, scenario 2. What if you're not actually told that you're at equilibrium? Then what do? How can you figure out if you are or you're not? Well, there's another calculation that we can do. It's actually really pretty easy. The system actually has to at least provide you an equilibrium constant in these cases. So oftentimes, if they don't tell you that you're at equilibrium, they at least have to provide the equilibrium constant. But this is not, you don't know yet whether or not you're at equilibrium. So again, what do? Well, we're going to have to calculate something called a Q. Now, a Q is a reaction quotient. Interestingly enough, it's calculated exactly the same way as a K value, but you're going to plug in concentrations that aren't necessarily equilibrium concentrations. Now, I know this makes no sense right now, so let's hop right into an example problem so I can show you. Let's take a look at the same equation, but this time the problem has changed. If in the above mixture, K has a value of 0.21, and we're finding that the concentrations are what's listed below, is the mixture at equilibrium? Well, the easiest thing that you can do is to actually calculate the value of Q, the reaction quotient. Notice that it's calculated exactly the same way as K. It's still products divided by reactants, and the coefficients still become superscripts. Fill in those concentrations, and then finally calculate your K value. Now, notice here that Q is actually smaller than K, and this is why the K value has to be given to you. Right out of the gate, this should tell you something. We are not at equilibrium. If we were at equilibrium, Q would equal 0.21. It doesn't. It equals 0.09. But what's interesting about Q is this actually gives you a second layer of information. It actually also tells you which direction equilibrium is going to have to shift to get equilibrium back again, based upon whether Q is smaller or larger than K. Let me show you what I mean. So we know that Q and K are calculated the same way. We know that they're calculated by putting the concentration of the products divided by the concentration of the reactants. We also know that K is a fixed number. And let's just, for this example, say that we're given a K value of 1. Great. Well, let's say we calculated a Q, and that the Q value for this particular problem is 0.001. So in this case, Q is way smaller than K. Well, what does that mean? Number one, you're not at equilibrium. And number two, that means that your Q has a very small numerator. In other words, it doesn't have a lot of product. And it also has a very, very large denominator. In other words, it has a lot of reactant. So as far as we're concerned, how do we go back to restore that balance? Let's take a look at the general form of our equation again. A plus B makes C plus D. Well, that would simply mean that I would need to shift toward the product side. So slowly, as I shift toward the product side, I'm going to chew up my reactant and make more product. And this progress is going to stop once the value of Q is going to equal the value of K. Now, let's take another look at another example. Again, let's pretend our K value is 1, but this time let's take a look at a Q that's 1,000. Now, what does that mean? Q is way larger than K in this case. Number one, again, you're not at equilibrium. But what this also means is that you have a very large numerator in your calculation. We have a lot of product. We also have a very small denominator, meaning we don't have very much reactant. So in order to regain our balance, when we take a look at the overall equation, we're going to need to shift away from product and back toward reactant. So slowly but surely, the reverse reaction is going to kick into hyperdrive, and we're slowly going to push toward that reactant side, chewing up the products, making more reactants, until finally the value of Q will equal the value of K.